In this video, we're going to take a look at 3 quick examples to practice telling the difference when we end up with indeterminate form and when we end up with a limit that does not exist. So in part A, we've got the limit as x approaches 3 of x minus 3 over x plus 3. So I'm going to start just by taking 3 and plugging it into my function. If you're not sure where to start, that's always a good bet. So we're going to take x equals 3, plug it in. Got 3 minus 3 divided by 3 plus 3. Here I end up with 0 divided by 6. And this is actually somewhat of a trick question. Because last time, in the last video, we said, hey, if you end up with 0 divided by 0, that's indeterminate form. And if you have L divided by 0, that limit does not exist. Well, here in this case, I don't have either one of those things. I've got 0 in my numerator, but not in my denominator. And in this case, 0 divided by 6, that is simply just 0. So be careful here. That limit does exist, and its value is 0. Might be an easy mistake to make. But here in this case, we're just going to say that limit is 0. And that's it. Part B, we want to find the limit as x approaches 3 of x minus 3 over x squared minus 9. Now, I'm going to pretend that I don't notice that this can be factored, right? I might look at that denominator and say, well, that can be factored. And if you notice that, great. That's awesome. Go ahead and factor that. But let's try plugging this in first and see what happens. Here I'm going to have 3 minus 3 divided by 3 squared minus 9, which is 0 divided by 9 minus 9, which is 0 divided by 0. This is indeterminate form, which means we've got to go back and try something different. So those of you that might have noticed, hey, that denominator, that can be factored, let's go ahead and do that. Limit as x approaches 3, got x minus 3 divided by x plus 3 times x minus 3. In this case, I've got that common factor of x minus 3 in my numerator and my denominator, so I can cancel it out. And I'm left with limit as x approaches 3 of 1 over x plus 3. At this point, I'm going to take 3, plug it in for x, and we should have our limit then. 1 over 3 plus 3, that's equal to 1 over 6. So this limit does exist, and its value is 1/6. Lastly, in part C here, it says limit as x approaches 3 of x squared plus 9 over x minus 3. Now, you might be saying to yourself, oh, you got me last time, Mr. H. You're not going to get me this time. X squared minus 9, that factored. I'm going to go ahead and factor x squared plus 9. Well, I'm sorry to say that x squared plus 9 will not factor. That's what we call a prime polynomial. You don't necessarily have to know it. It's a fancy math term, but that numerator will not factor. If it was x squared minus 9, then yeah, sure, I could factor it. But in this case, I can't. And because I can't factor it, I can't simplify or anything, I'm just going to plug 3 in. So let's see, I'm going to have 3 squared plus 9 divided by 3 minus 3. Here I've got 9 plus 9 over 0, which is 18 divided by 0. This time I have 0 in my denominator, but not in my numerator, so that means that this limit does not exist. No more work needs to be done. Now, it turns out there's actually pretty interesting behavior going on at x equals 3, and in the next section, we're going to take a look at, can we say a little bit more about this? Sure that the limit does not exist, but is it possible to say more about what's going on at x equals 3? And well, I'm just going to have to leave it on a cliffhanger there. You'll just have to sit tight and wait till section 2.2 to find out.